Ah, much better. Yeah, that's good.
Professor,
Yes.
my name is Lena.
Hi,
I
Lena.
emailed you
Oh,
before.
yeah, yes. I
Nice to
remember.
meet you.
Nice to
in
meet
person,
you.
finally.
Great, great. I'm here tomorrow as well.
Oh, really?
So if you want to catch me, I'm
Are you-
usually hanging out with Stefan.
Because Stefan actually mentioned that he's probably gonna invite you to our QFT class or something.
To what
To our
class?
QFT class.
Oh, he didn't tell me
Or-
about
I'm,
that.
I'm not
but-
sure. I'm not sure. Though.
Okay, sure. I'll come. I'll come by. Where's that? When's that? Tomorrow?
Yeah, tomorrow at like 2:30. I think.
Sounds good to me. Nice to meet you in person.
Nice to meet you.
Just gotta check to the 3 foot height.
Sir, good to see you. You got to be so. I'm going to send you a draft of the paper. I'm going to be so happy to see you.
Say it again. Yeah, especially the near range. That's the near range. Good.
Oh no, this is water. This is water.
Come on, just skip the line. What you want?
There's only one.
The last school I was at, that's what we did.
Oh, wow.
That's going to be the difference between Brown and Penn State.
You gotta keep the grass.
Yeah. What about ASU? You guys,
What?
Professor skip lines?
There isn't even a line. It's kind of this general melee of trying amorphous blob trying to get their coffee.
Where's this guy? Are you working today?
Maybe you
Ask him. He's not here.
some coffee and then
Reveal all your slides.
Oh yeah, shoot. I shouldn't do that. definitely don't want to do that. How do I go back quickly?
Okay. Where's help? He just disappeared.
He's back there.
Where?
In the
Excuse me. Oh.
corner.
All right, we're about to begin. As soon as this mic starts working. Well, I don't think I need it. Yeah. You might need it.
I have a mic.
Oh, you have a mic. Okay.
I don't know if it's on.
Okay.
What? The coffee? No. They're taking the coffee away. Should I?
Maybe the coffee's all gone. Okay. So I know it's this time of year where we're all excited and jumping around, and the energy is so high. It's the time of year, so let's give it up for that. Yeah. Okay. And so we can't think of a better time of year to have this esteemed guest of ours. I want to say a few words about him. So Maulik, I met Maulik 24 years ago, actually. We were both visiting postdocs at Columbia University when Brian Greene started his group out there. And I remember him being this erudite, well-dressed, well-spoken, giving these amazing talks ahead of his time. You were back then talking about de Sitter space 24 years ago. Now people elsewhere are talking about de Sitter space. So let's see, a few things about Maulik. He lived in Albert Einstein's house for 2 days, where he house sat with a frog, a few dogs, and...
A dog, 2 cats, a frog, and a snake.
Okay, very good. Okay, some formal things about him. He did his undergraduate at UC Berkeley, his PhD at Princeton with Frank Wilczek. For those of you who know who Frank Wilczek is, I hope you all know who he is. Wrote some amazing paper, and I consider him to be one of the top people in my generation in the field of gravitational physics and other things, and he's going to tell us about that today, Maulik.
All right.
Oh, one last thing. I would love to give a warm welcome to our new faculty member, condensed matter theorist, Aaron Hui. Aaron, raise your hand. Welcome. We're excited to have you.
I don't need this. All right, can you hear me? I don't know if this is on. Is it on? Okay, it's on. All right, well, thank you for that introduction and for warming up the crowd. So it's great to be back at Brown. I don't think I've been here in about 20 years. So this is nice to be giving a colloquium here. Okay, free falling in quantum space-time. It's been over 100 years since Albert Einstein, the great Albert Einstein, gifted us his magnificent general theory of relativity. And in all that time, Einstein's theory has successfully accounted for every single observation about gravity ever made. Frankly, that's a little bit surprising because we know that Einstein's theory is not complete. It predicts singularities, which is indicative of its own problems with the theory. And moreover, it's a classical theory, and we know that ultimately gravity should be quantized. So today, I would like to tell you a little bit about very exciting recent developments in quantum gravity, and incredibly about potentially observational signatures of quantum gravity. To be honest, I never thought I'd say that combination of words. But there are we may in fact be on the cusp of being able to detect some indications that gravity is in fact quantized. And to give away my punchline, what we're going to find is that the trajectories of freely falling objects, when gravity is quantized, space-time starts fluctuating, and they acquire this kind of random motion, this noise. And you can think of that random motion as a bombardment of the falling particles by gravitons. And here, oops, hold on, what happened here? There's supposed to be an animation here. Well, why is my animation not happening? It's automatically going to the next slide. Okay, imagine a falling apple. Right, so this is an artist illustration of an apple that's being bombarded by triangular gravitons. Anyway, before we get to all that, and since this is a broad audience, I'm going to give you a gentle overview of what it is that we know about the nature of gravity. All right, so let me tell you then about the story of gravity. Sit back and relax. Our story begins in 1666, a moment in history that was oddly similar to our own time. There was an epidemic of the bubonic plague sweeping through England, and Cambridge University was closed for 2 years. All of England was under lockdown. They had lockdowns, they had social distancing, they had quarantines, the works. The only thing they didn't have were vaccines. And they just had to wait for the epidemic to go away, okay? Which they did. They waited for 2 years. Cambridge University tried to open a little bit too early, and then the faculty all died of plague. So, yeah, not a good idea. Anyway, but a young Isaac Newton, who was then a 21-year-old student, spent his time wandering through apple orchards, rather fruitfully, and discovered in the process his universal law of gravitation. With just a single equation, Newton was able to account for a sweeping range of gravitational phenomena. His law was truly universal. This is all from one equation, right? Okay. But for all its power, Newton's theory had some imperfections, and I want to tell you about those. You see, Newton could explain how strong the force of gravity is, but he couldn't really say how it was that gravity worked its magic. For example, the sun exerts a gravitational pull on the Earth, but how does it do that? It's 150 million kilometers away. How can the sun exert any pull if all there is between the sun and the Earth is empty space? This is how Newton put it. It is inconceivable that inanimate matter should affect other matter without mutual contact. Gravity must be caused by an agent, but whether this agent be material or immaterial, I have left to the consideration of my readers. This is one of those annoying, those annoying textbooks where the interesting problems are left to the reader. That's sort of what Newton did here. Okay, so what was the agent that transmitted the force of gravity? Well, actually, in electrodynamics, there's a similar story. Newton's law of gravitation, of course, looks a lot like Coulomb's law. And this is totally ahistorical here, but in E&M, if you start with Poisson's equation, add special relativity, charge conservation, or gauge invariance, if you like, then you'll recover. From that, you can actually obtain Maxwell's equations. That's, of course, not how they were derived, but you can do that. And the upshot here is that in E&M, the forces are transmitted causally by electromagnetic fields. So that's what's transmitting the force. It's not just that there are charges separated, but there's a field, and it's the field that's responsible for transmitting that force. And so maybe the same is true in gravity. Okay. However, if one were to try the same thing with gravity, if you took Newton's law plus special relativity plus, instead of charge conservation, energy momentum conservation or gauge invariance, you don't recover the modern theory of gravity, namely Einstein's equations. Something else is missing. If you did this for the experts in the field, you'll only get linearized gravity. Okay. Actually, Newton's theory is another problem. Well, not problem, but a puzzle. So long ago, Galileo performed a famous experiment, and here he is. There's a very romantic picture of him. in which he's holding a cannonball in one hand and a musket ball that's a kind of spherical bullet in the other hand, and he drops them both from the Tower of Pisa, and of course, as we know, they land at the same time. So that's quite remarkable, and it's a consequence. Do I have a pointer? What is this? No. Is there no laser pointer? Well, I'll point with my finger then. Oh, yes. All right, great. Thank you. Okay, so this is a consequence, or even better, so you have F equals ma, you have F equals mg, and equating these two, you can see that the m's drop out, and so A equals g. All right? But that's kind of remarkable. It tells you that the acceleration only depends on this external gravitational field g, and doesn't depend on any property of the falling object. Okay? And just to look at how different that is from, look at what the story looks like in ENM. If in ENM, if you have F equals ma and then F equals QE, okay, then solving for A, you see that it depends on both the charge and the mass of the object that's falling. For centuries, this remained a curious fact about gravity until in November of 1907, Albert Einstein, while daydreaming about gravity, as one does, suddenly had a flash of insight in what he called the happiest thought of his life. And he realized that Galileo's experiment was the key to unlocking the mystery of what gravity really was. So basically, here's what it says. Well, here's a clue. Okay, so if you take two objects and drop them straight down, okay, so they're falling down in the z direction vertically, okay, parallel, eventually they start coming closer together as they are drawn towards the center of the Earth. Okay, so although they start out parallel, it's not visible in this picture, but yeah, they start out parallel, but then they converge. Well, where have we seen that before? If you take two lines that start off at the equator to go straight down the longitudes that go parallel south, let's say, those two straight lines eventually converge at the South Pole. Now, in the case of the Earth, that's obviously happening because the Earth is curved, right? So the parallel lines don't obey Euclid's axioms, and instead they converge. But hey, how do we know that this isn't curved as well, right? There are no helpful grid lines drawn in space. And so what Einstein sort of realized is that somehow space, and space-time actually, is also curved. And the only thing that could have curved it is this massive object here. So right away, Einstein realized that it's actually space itself, through its curvature, that transmits the force of gravity. Motion is determined not by any properties of the objects, but it's determined by space-time. Space-time is the agent that Newton was looking for. And just like that, Einstein turned the study of gravity, which would have just been yet another force, into the study of nothing less than space and time. One extraordinary consequence of this kind of view of thinking about gravity is that since gravity is a distortion of space and time, everything is affected by gravity, okay? Including light. Light is affected by gravity. Why? Because light lives in space. Light moves through space-time as well. So if space-time is distorted, light will also be affected. And here's some classic pictures. This is called an Einstein ring. So here there appears to be a circle. This is not created. This image is of a single object that's behind this central object. And it's not created by some funny lens, but it's actually lensed by space-time itself, by curvature of space-time. So according to Einstein's theory, his general theory of gravity, his general theory of relativity, space is also not fixed or rigid. It's flexible, like an invisible, malleable medium. It can bend, stretch, squeeze, warp. And it's the shape of space that we interpret as the force of gravity. Einstein also predicted the existence of gravitational waves, which probably, it worked. This animation worked. Okay. So when you jostle space-time, you'll create a disturbance in the force, which then spreads out and appears to us as a gravitational wave. Okay? So what's the gravitational wave do? The gravitational wave is a ripple in space-time itself. And so what it does is that everything that's living in space-time, which is basically everything, all distances are affected by this wave of space that's passing through. Okay, so for example, So if a gravitational wave passes by, a ring of satellites would be deformed like this, attracted in one direction, stretched in one direction, and compressed in another. Okay, and that's sort of what would happen. Okay, so when a gravitational wave passes through us, we're made slightly taller and shorter as the wave passes through us. Okay, but by a very, very, very tiny amount, like far smaller than the size of an atom. So these gravitational waves, as you probably all know, have recently been detected. This is LIGO, the Laser Interferometer Gravitational Observatory, there's one in Hanford, Washington, and Livingston, Louisiana. And what it basically is they're sort of 4-kilometer long arms, and there are mirrors on the opposite at the ends of those arms, and we're measuring with a laser the time of flight of these of photons as they go back and forth between these arms, and they interfere over here in the center. And if a gravitational wave passes through, one of the arms is going to get longer, and the other one's going to get shorter, and that's going to affect the interference pattern because it's going to take longer to go down for the light to go here and shorter for it to come back here, so it'll be out of phase, causing an interference effect over here. Okay. And so the time variation of the length tells us about the source that created the gravitational waves. Okay, so Einstein's theory too, like Newton's before it, explains a host of phenomena from the Big Bang to black holes. Unlike Newton's theory, it tells you the underlying mechanism of gravity. As I said, it predicts the bending of light. It contains black holes. Predicts, of course, the orbits of the planets, including corrections to Newton's laws. At the expansion of the universe, as I said, we have gravitational waves. And we even use Einstein's theory in GPS, so when you want to find your way to the nearest Starbucks, you can thank Albert. Okay. But despite all these great successes, Einstein's theory, like Newton's before it, has some imperfections. Okay, and the main one is that it's just a classical theory. And we know that our ultimate theory of the universe has to be ultimate theory of physics, framework for physics is quantum mechanical, and so we should have a quantum description of gravity. And Einstein's theory is not that. Moreover, it contains, I won't say anything more about this, but it also contains singularities, which are a sign that there's something wrong with the theory. Okay. So that's my background about gravity. Now I want to tell you just a little bit about quantum mechanics and quantum field theory, only enough for us to anticipate what quantum gravity should be about. All right. So in quantum mechanics, of course, the outcomes of experiments are probabilistic. Okay, you do the same experiment many, many, many times, and you get different results. Okay? Things fluctuate. For example, the electron here exists in a fuzzy haze of possibilities with both its speed and its position blurry and indefinite, as shown in the simulation of an electron and hydrogen atom. I don't remember what state it's in, but that's an electron. Okay, that's the probability distribution of the electron. Okay. In addition, quantum field theory, which is like the relativistic version of quantum mechanics, tells us more. It tells us that the world is made up of identical particles, and that forces also have particles associated with them. So here's another way of thinking about force, that forces are transmitted by certain particles that mediate the force. Yeah, so for example, the electromagnetic field is made up of photons, and those are the force-mediating quanta of electromagnetism. Okay, the photons become apparent at low light. So low photon statistics allows for significant relative fluctuations, and that results in graininess or noise in photographs. So here we have a picture, and now we've dimmed the brightness of this picture. And if we do that, it's not just that the picture becomes darker, but it also becomes grainier. Okay? It becomes noisier. So the existence of these photons is apparent as random fluctuations or noise. You can get a speckle pattern or something. In fact, if you, even with your iPhone, with an old iPhone at least, the newer ones have all kinds of noise correcting software. But you could take a picture of something in low light, and you'll see little dots, and that's if you take a picture of something that's really dark with very low light, like you lock yourself in a room and turn off the light and take a picture. There are actually, if you think about it, there are only very, very few photons, only a handful of photons that hit a particular pixel in your sensor while the shutter is open. And so the number of photons is so it's in the tens, so that any little fluctuation in there will be either interpreted as a signal or not. So you see sort of graininess, and that's just because of the randomness of photons. Okay. All right. Now at last, let's turn to quantum gravity. So what would a theory of quantum gravity say? And here we'll be agnostic about what the ultimate theory of quantum gravity is, whether it's most probably string theory. Okay. But we know that there should be some regime, some in which quantum gravity can be thought of as a field theory. Okay, and if that's true, then we can use the ideas that we had earlier and say that there should be a hypothetical particle called a graviton that will mediate the force of gravity, just like there's photons that mediate the force of E&M. And we also expect that space and time should be uncertain and randomly fluctuating. So that's sort of the expectation. We expect that gravitons will create noise in those fluctuations, just like the photons did in that picture. Okay? All right. So now I want to tell you about, this is the heart of this talk. What would the observational signatures of quantum gravity be? Okay. So before we even approach that question, let's ask generally, how do we probe gravity? Okay. We don't just go out there and measure the gravitational field. How do we actually probe the gravity? And we do it much the same way that Newton did. Newton watched something fall. Okay. So he watched an apple fall, according to legend. And so the way to detect gravity, the way to probe gravity is to look at the free-falling objects. The technical term for the paths of free-falling objects is geodesics. And so we're interested in the geodesics of a falling apple, or the geodesic of orbiting Mercury, or the geodesic of receding galaxies, or the geodesic of bending light. Okay? So what we want to know is what happens to those geodesics that we observe when gravity is quantized, when space and time are regarded as a quantum field, when the gravitational field is regarded as a quantum field. So when the objects are free-falling in quantum space-time, if you will. Okay, so single geodesics don't tell us that much, it turns out, but pairs of geodesics do. And this is a classic concept in general relativity called geodesic deviation. So imagine there are two free-falling particles, m and m naught. We can attach our coordinates, origin of our coordinates to capital M here. So that stays at the origin, because we can free to pick our origin. And then the distance to the other one, which is now the position, since this is at the origin now, this is the position of the other particle, xi. That position becomes is what's called a geodesic deviation. Okay, it's the separation between these two things. Now, if there was no gravity, if there were just two objects in flat space, okay, in ordinary space, they would just move on straight lines, all right, in space-time. Their world lines would just be straight lines, and their geodesic distance would just be a constant, okay? Or maybe it will grow linearly if they have some relative velocity. But if you just leave two objects at rest, they're just going to, and without gravity, they would just stay in the same position in space, and so there'd be some fixed xi, some fixed geodesic deviation vector. So that's exactly what we measure at these detectors. If you can think of one of the mirrors of LIGO as one of these masses m, and the other one as some other mass m naught over here. So there are two mirrors, which are like 40 kilogram mirrors, and then xi here is their geodesic separate distance. Okay, so that's actually what we're measuring in these gravitational wave observatories. Okay. All right. So. Now we get to some equations. In general relativity, there's a famous equation called the geodesic deviation equation, which relates the behavior of the geodesic deviation, which is xi here. Okay, mu refers to its indices in space-time, and it's related to the curvature of space-time encoded in this object called the Riemann tensor. So I'm just going to write it this way, okay, dropping all the indices. And so what this is telling you is that if there's a gravitational wave passing by with amplitude h, okay? So remember the gravitational waves cause things to stretch and squeeze. So that's going to cause this geodesic deviation to increase and decrease. It's going to cause it to fluctuate. So as one of these waves passes by, then the geodesic deviation changes in time. Okay? So here's our equation. All right? But this is classical. And what we want to know is what is the generalization of this equation when the space-time metric is treated as a quantum field. So my collaborators and I, this is Frank Wilczek, and this was my former postdoc, George Zahariade, who's now faculty in Poland. We decided to think about this problem, and we quickly realized that it's not clear what would happen. Right? And so we decided we'll start from first principles, and for theorists, first principles means writing down an action and writing down a Lagrangian. So we did that. We considered the action for gravity coupled to two free-falling particles. Then we expanded the fluctuations of the gravitational field in Fourier modes. Okay? I won't give you all the technical details because this is a colloquium, but I will put this next slide on because the result is quite nice. So here we've just to give you an idea, we focused on a single gravitational wave mode. Okay, so imagine a gravitational mode, a mode of the gravitational field, which has frequency omega and amplitude q. Okay, so it's a cosine or sine or something, or it has a frequency and an amplitude. This is how what the action looks like. So this is the mode has amplitude q, it has frequency omega, so the amplitude can change in time. That's why it's like this. And you can see that this part here just looks like this is a Lagrangian for a simple harmonic oscillator, right? T minus v here. And then the position of the second particle is just given by 1/2 m xi x dot squared. That's like a free particle Lagrangian. And then finally, there's a coupling. And that coupling comes from the gravitational interaction. Okay, so there's a very strange looking coupling because it has derivatives in it, but that's what it is. Okay, so this is an amazingly simple action, actually, because harmonic oscillator plus free particle plus, okay, coupling. But the important thing here is that it's an action that's quadratic in Q as well as quadratic in psi. And because it's quadratic, it can be solved exactly, not just perturbatively. So we were able to solve this theory. This theory is not the full theory because we have restricted to linearized gravity, but we were able to solve it exactly. So I just want to, no longer able to step forward here. So I'll just outline what we did. We said let the gravitational field initially be in the state psi, and we don't know what the final state of the field is because it's interacting in some way. And the particle, the second mirror, we'll let it also be in some quantum state, and originally in state A, then is going to go to state B in some time t. And so what we want to calculate is this transition probability of the particle going from state A to state B in the presence of a gravitational field that's initially in state psi. And because we don't know, so it's a probability, so it's a square of an amplitude. So initially the state is here, psi, the field is in state psi, the particle is in state A. Then you do time evolve forward with this unitary time evolution operator. And then the final state is particle in state B and field in state F. And we're going to square it because of the probability, and we don't know what the final state is, so we're going to sum over all the final states. Got it? So that's what we're doing. It's just ordinary quantum mechanics. And like I said, we can do it exactly. And here it is. And it's a mess, right? But here it is. The point about showing this is just so that you know that we can compute the transition probability exactly. This was done using techniques developed by Feynman and Vernon. I'm only displaying this here to show that it can be done. But ultimately, we're not interested in this huge mess, okay? Because we want to treat the mirror, the second particle, classically. It's 40 kilograms, right? So we don't need to treat it quantum mechanically. So let's just say, let's take the classical limit of this. So when we do that, here's what we get. So this is the location of the second mirror. The first one is we've chosen to be at the origin, and then there's another particle. They have a geodesic deviation psi. And this is the behavior of psi. There's the original 1/2 h double dot from any classical gravitational wave that there is. There's this complicated radiation reaction term, which is similar to the term that you find in ENM, the Abraham-Lorentz force. I won't say anything more about that. But most interestingly, there's a noise term. Okay? So this equation has a random noise in there. Now, why is there a random function in there? Well, if you take a classical object, classical system, and you couple it to a quantum system, right? And then even if you're not paying attention to the quantum system and just looking at the classical system, the probabilistic nature of the quantum system will imprint itself on the classical system that you are watching, and that will then become stochastic. It'll become probabilistic. So even though we're looking at a classical system, it's no longer deterministic because it's coupled to a quantum system. Okay, so in this case, we've coupled a quantum gravitational field to a classical separation of these two particles. So this is the noise of the gravitational field, and the statistical properties of this noise depend on the quantum state of the gravitational field and can all be calculated. And I just want to compare it with the original equation. This is what we had originally. Now we have this. Okay? So schematically, this is what it happens. So imagine you have, this is a space-time diagram. Time runs up. Imagine you have two particles. They're whirl lines. If there had been a classical gravitational wave, they're whirl lines, which would, without the gravitational wave, they would just go straight up in time. But now, because there's a gravitational wave that's causing space to stretch and squeeze, they're going to do this. Okay? This is what would happen classically. And quantum mechanically, this is what would happen. We will have not just the classical gravitational wave, but there's a random noise which adds this kind of jitter. Okay? So if we detect this kind of jitter, that would be a key indication that particles, that space-time is quantized. So here's the takeaway. The signal of quantum gravity is in the noise. There's a fundamental noise that should be present in gravitational wave interferometers that has its origin, whose origin are the quantum fluctuations of space-time. Okay? I should say that the study of noise has played a critical role in the history of physics. It was excess noise in a radio receiver that led Penzias and Wilson to discover the cosmic microwave background. It was Brownian noise that led Einstein, that resulted in Brownian motion, that led Einstein and Smoluchowski to interpret that noise as the existence of molecules, with the discreteness of matter, as it were. And it was shot noise that led to the discovery of fractionally charged quasi-particles. So again and again, noise has played a very important role in physics, and it would be poetically beautiful if the noise at gravitational wave interferometers, which they're right now trying to get rid of because they're focusing on the signal, but if that noise, if we looked at it properly, would encode the discreteness of space and time. Okay. So that's the main message. Now, can we actually observe this? Can we, in fact, detect this noise? In order for the noise to be detectable, we need two things. First of all, there's tons of other noise too, which is not so interesting, right? There's thermal noise. There's shock noise from the photons that are in the lasers. There's noise in the electronics that they have. There's seismic noise from a truck passing by, right? There's all kinds of noise in their system. And so we need to be able to distinguish it from that kind of, omnipresent noise that's not of any deep quantum gravitational origin. And in addition, the amplitude better not be too small. The fluctuations are Planck length. Great, we'll never see those, right? So how do we actually observe this? Well, so first of all, remember that this is a stretching of space and time. So the gravitational field squeezes this way and compresses that way, or vice versa, stretches and squeezes in opposite directions. So because of that, there are angular correlations. So if it's in what's happening in with the detectors. And it turns out that the noise correlation has this kind of angular behavior. Okay, so if you have two different detectors with some angle theta, then the noise is correlated like so. So it's perfectly correlated if the two detectors are aligned in the same way. But if they're at an angle of 54.7 degrees, which is where 3 cos squared theta minus 1 is 0, then they're not correlated at all. Okay. So this is nice because it gives you a way of a kind of a way to isolate the quantum gravitational noise. Imagine you have 3 detectors, 3 arms, and you're measuring the fluctuations of those arms, and there's noise in their lengths, and 2 of them are aligned, and the third one is off at 54.7 degrees. If we find noise that is correlated in all 3 detectors, it's not quantum gravitational noise because it's not supposed to be here. But if, on the other hand, these 2 are correlated, and we find noise in these 2 that are correlated, but no correlation between these 2, then that would be quantum gravitational noise. Okay, most of the noise in these detectors is not even correlated, right? So, for example, photon shot noise. If there's photons bouncing off in one arm and some other photons bouncing off in another arm, those are not correlated at all. So there's only a small number of the original noises that are correlated in the first place, and this is a way to eliminate even those. Okay? Great. Now, what about the amplitude? Well, the noise amplitude, turns out it depends on the quantum state as well as on the detector, and it depends on the power spectrum depends on the state, but generically, the noise amplitude diverges. So it's not intrinsically small at all. The only reason it's small is that we have a cutoff because we're only sensitive to certain frequencies. Okay, it's a bit like, I don't know if you know about this, the Casimir effect, which really depends on the size of the system that you choose, and the amount of this effect depends on the size of the system, or in this case, your sensitivity in omega. Moreover, we have some indications that the fluctuations actually grow with time. So you leave these particles together and you let them go, and then you see what their distance looks like as a function of time, and it increases in time. That's actually very similar to Brownian motion, where the variance increases as linearly in time. Here it's even better, it grows quadratically in time. Okay? The best case scenario is that the state itself is some exotic state. So the gravitational field is in some state. Okay, we've quantized it, so we need to put it in some kind of quantum state. And if it's not in a state that looks very classical, if it's not in a coherent state, if it's in a state something called a squeeze state, then there's an exponential enhancement in the amplitude of the noise. Okay? And squeeze states are naturally produced in gravity because gravity has nonlinearities, so we expect them to be generated by merging black holes and also by inflation. Okay, so this is my last slide, pretty much. I just want to summarize. Quantum fluctuations of space-time, okay, when we quantize gravity, produce noise in the separation of free-falling particles. We probe gravity through the behavior of geodesics, of free-falling particles. And when we probe the separation of those particles, we'll find that not only do we have this original term from classical gravitational waves, but there's also this random fluctuating term. Okay? And the characteristics of the noise depend on the quantum state of gravity. Okay, in a way that's calculable. We were able to calculate all the statistical properties of this noise, its variance, its autocorrelation, and so on, for thermal states, squeeze states, coherent states, vacuum state. And depending on the quantum state and also on the experimental sensitivity of detectors, the enhanced noise might be observable. Okay, so that's what I would say. Thanks for listening.
So, any questions? Hopefully, we get a lot of them.
Thank you so much for excellent talk. I'm just, from an experimental point of view, what the frequency spectrum, is it white?
It's actually a linear power spectrum. For the vacuum, it's just a linear power spectrum.
And for a specific sort of example, are you able to give an illustration of what the strength or the amplitude of the noise is likely to be? So I couldn't see anywhere a number that I
didn't put a number on because this part is not yet settled.
Oh, I see.
So we did some preliminary calculations that found that the noise for vacuum states and coherent states would be unmeasurably small, like Planckian, which is maybe not surprising. And then, so that would mean that our only hope really would be something really exotic like squeeze states. So if the gravitational field were for some reason in a squeeze state, we'd hope to see it. So we have to hope that nature is kind enough to give us these kinds of states. But now we've grown a little more optimistic because we found that there's actually a term in the variance that just grows with time. And I don't want to put too strong an emphasis on this because we're still unsure whether this is real or it's an artifact of perturbation theory. But so if that's true, then it would behave a bit like Brownian motion, where the variance just grows in time, and that would make it much easier to observe.
Yeah. Thank you. Okay. Getting the board there.
So to put a number in it, even for the vacuum in that case, if you let something, if you have two mirrors that are a few meters apart, two particles that are, and you let them go, and then you measure their variance 15 minutes later, it'll be about 10 to the minus 21 meters, okay, which is measurable. They're a few meters apart. Yeah. Yes. Yeah. It's a tabletop experiment. It's better the smaller the equipment, the smaller the arm, because there are more and more gravitational modes that contribute because the UV cutoff is higher. So it's LIGO is not the best place to look for it, but tabletop experiments. Yeah. Yeah. Is achievable. Yeah.
Would
Don't
we
hold me
expect
to that. This is just
Would we expect corrections to these results based on the fact that the mirrors in a LIGO detector are not in free fall and are being suspended in a gravitational field?
So they are in free fall in the XY direction. They're not free fall in this direction, but they're free to move in the direction along the arm.
Hi, this is really fun. I found myself just stuck a little earlier in the talk. So you gave the photon noise, that picture with the speckle, which physically seems a little bit different from the type of interactions you're talking about here. So what is the analog in electricity and magnetism to photons, like peppering, electrons? Or
So we don't measure light the same way we measure gravity. We absorb the light. Yeah. I don't know about that, but yeah, we absorb the light, right? Whereas for gravitational waves, we're sort of sensitive to the amplitude fluctuations. So I'm not sure how to make an exact parallel between the noise effect that we see in a photograph, which is absorption, versus the noise that we would see in these amplitude fluctuations.
I got a little bit lost. You said in the figure you had, you needed 3 arms and find correlation in 2 of them.
Yes.
That would be a signal. But LIGO and Virgo and everyone, they have 2 arms here. So are you looking toward Lisa, maybe, with this?
So my model detector is just 1 arm, right? Now, in an ideal world, we could measure the length of that arm precisely, right? And then that would be the analog of the most basic gravitational wave detector you can have is two falling particles that creates an arm, and you measure the length of that arm. That's not how a real detector works. LIGO has 2 arms because they can't measure this. They need to interfere it with another arm to see the relative changes. So our model doesn't exactly what people actually measure. This is a theoretical. It's like Einstein's light clock or something. But to connect to an actual gravitational wave equipment, we need to play around with this a little bit. So the example with the three arms was if we could measure the lengths of these arms independently without having to have another orthogonal arm, we would need 3, 2 parallel and 1 at 57 degrees, and then there would be, yeah.
Hi, thanks for the nice talk. I just wanted to ask if you could clarify a little bit about the difference between this type of noise and just regular shot noise. Should I really be thinking of this as some like classically large number of gravitons going through, and then you'll have some kind of shot noise measurement in your detector here, or is it something that's slightly different? Like the gravitons are interacting.
I don't think it can be viewed as shot noise.
Okay.
It's not the shot noise of gravitons, and we were confused for a long time about that. We tried to originally estimate what that shot noise would be, but again, the gravitons aren't measured that way. And even the word graviton, I'm using it rather loosely. What I really did was I took the metric, quantized it, and integrated it out, as it were, and looked at what the behavior was on the thing. So we didn't think about it in terms of individual gravitons. So
I see. Thanks.
Sorry, and when you said minutes, does that mean we have to measure the length over many minutes at the 10 to the minus 21 meter level? You said in order to get this, because obviously from an Earth-based frequency point of view, that's quite challenging in terms of. But that would need to be the requirement. Is you're measuring some absolute way how much the distance is changing over many minutes is.
yes.
Yes. Okay.
Yes.
Yeah, I just wanted to clarify.
Yeah.
Thank you. Yeah.
And then you'd have to do that again and again and again to see the variance in the thing.
But you need that correlation.
Yes.
Thanks for the great talk. You mentioned that the action and all the calculations after that was for a linearized gravitational field. So maybe this isn't very realistic, but if it was strong enough that you can't make that assumption, how would that affect the noise term that shows up in the classical limit?
All hell would break loose because if you start adding more terms in gravity, the theory becomes problematic in many ways. So gravity can't really be expressed as a quantum field theory. And so we'd have problems from lack of renormalization. Yeah, so those are the kind of things that would go wrong. Also, we sort of assumed that the modes, that we're in a small enough region that we can ignore the curvatures, and that the modes are the same. The fluctuation, it's called, like in ENM, we use something called the dipole approximation. So this is similar to that, where the modes are considered to be such that there's the same amplitude for the two different particles. But if there was high curvature, we couldn't assume that.
Thank you for the talk. It was very, very insightful and interesting. So if this noise can be observed in a detector, would any information about kind of the structure of the model of quantized gravity, would that be able to be extracted from this signal, or would just the existence of quantized gravity be able to be validated?
Oh, I think it would be amazing, because we would so right now, when we see classical gravitational waves, what does that tell us? Well, the form of the classical gravitational wave is telling us about the source of the gravitational wave, right? So the different spectra of the classical gravitational wave will tell you whether it was, created by two neutron stars merging or two black holes merging. They have a distinct signature, right? The same will be true for quantum states. If we got different kinds of noise, you would define the different spectrum of the noise, you would sort of see, the physics. You might learn about the physics that produce that kind of state. If it was Hawking radiation from not that that's something we're going to see, but if it was, then there would be a particular thermal noise which has its own kind of. So to tell us what the most interesting thing is if it's squeezed states, because then we can learn about strong field gravity, quantum gravity. So, yeah.
Okay, let's thank our speaker again. Don't leave yet. I was told by our chairperson, and we must listen to her when she asks us to do something, and I like that too. So, because what I'm about to tell you is actually really cool. So next week, we have our sort of like, I don't know what to call it. It's like the big talk of the year. Not that your talk wasn't the big talk of the year either. But we have the E.O. Wilson. This is like sort of the biggest talk in the physics department offers. It happens once a year. The deliberation process is very, testy and all that stuff. And we are pleased to have Greg Gabadadze, who is the Dean of Sciences at NYU and also leads the MPS for Physics for the Simons Foundation. So please, we want a really good turnout, okay? So we need that ducat. You know what ducat means? Anyway, so next week, Greg Gabadadze will be speaking this Monday, and you will get all the nice advertisements. Thank you, and thanks again.